Hi, this is Bob from racecarbook.com or airdensityonline.com. We're going to illustrate using Pro-Calc to set up a new baseline profile for a land speed record high altitude combination, such as Bonneville. We're going to start out and see what we can get in the way of sample baselines that might be close to that. I don't see anything in this list. Let's go for a description. So I'm going to go into the info. Sample baselines normally aspirated. Okay. It looks as though these are all V8s. However, what is significant is the engine that we're going to be doing is a 300 cubic inch inline 6, and it's going to be running between 7,000 and 8,000 RPM. And we're going to be using up and down nozzles in this combination. So let's see if we have anything on this list that might help us out. Well, a 300 cubic inch 6-cylinder is about 50 cubic inches per cylinder. And a V8 of that is 400 cubic inches. So our normally aspirated 410 torque peak, again, if we started out with a horsepower peak, that involves a 410 running methanol at the horsepower peak with high speed. And again, I don't want to start out with the high speed. In fact, we're not going to use a high speed with an RPM range between 7 and 8,000 RPM. We're simply going to jet it with the main for that RPM range. So we're going to go down here to the NA 410 torque peak, and that is without a high speed. And that looks like that might be closest to what we're going to do, and then we're going to use Pro-Calc to modify that to get us where we're at. Okay, going back to our baseline profiles, we're going to select 410 torque peak, add baseline. Now this is an 8-cylinder combination, so we have to change it. So I'm going to change the title to 300. I'm going to delete torque peak and just put land speed. Okay, coming down to our setting up our profile, I'm going to put in 300 cubic inches. This has a very expensive high-flowing cylinder head, so we're going to leave 110 for the volumetric efficiency. The fuel pump, we have to select a fuel pump. So I go to my fuel pump list, and we have a used Hilborn -0. So we come down here to our Hilborn -0, and it's a 3.34 for the fuel pump entry. 3.52 for a new one, 3.34 for a used one. Okay, at how many RPM? 8,000 RPM, that is again a pump rating. Just a reminder, Hilborn sizes their pumps at a different RPM, normally 1,800, and you have to size it up for the 4,000 RPM range if the pump runs at 1/2 engine speed, which is say 8,000 RPM. Now this is not 8 cylinders, it's going to be 6. So I'm going to change that to 6. We're going to be using up and down nozzles, so we're going to leave 2 nozzles per cylinder. I have no idea what the main is going to be, so I'm just going to put 100 in there as a guess. We're not going to run a high speed, and we're not going to run a pump loop or second high speed. I don't know what the pressure is, so I'm going to leave that blank. Now our target RPM, we're going to move that up to 7,000 RPM because that's the range we're going to be running, 7 to 8,000 RPM. We're not running any nitro. And looking at the local weather forecasts from a source such as airdensityonline.com tracks for Bonneville, the temperature typically would be 90 degrees for race day in the summer. The humidity is going to be around 20%. And the uncorrected barometer is about 24.5. This is way up there. Again, if I had the corrected barometer like 29.92, I'd need to put the elevation in there, whatever Bonneville is. I think it's 4,500 or 5,000 feet, something like that. But if I have the uncorrected barometer, I just put that value in, and I do not put an elevation in there. Okay, now this nozzle selection was for an engine with 50 cubic inches per cylinder, so I'm going to leave that alone. Let's go ahead and set up our baseline profile. Now that shows 8 nozzles, but when I create this, okay, now that's giving me a 5.42 air to fuel ratio, and that's actually pretty good as a first shot. Go back to edit this baseline and let's examine what that is. Okay, sure enough, I've got my 6 nozzle combination. Okay, well that's pretty interesting. That was a guesstimate with a 100 thousandths main bypass. That's our baseline. Now I'm going to go to air-fuel ratio calculator. And that's the only profile, so that's come up. Okay, so I'm using that. And then I got to re-enter my weather. Again, the jetting calculators do not pull the weather out of the baseline. You have to re-enter that. So that'll be 90 degrees. Humidity is 20%, and the barometer uncorrected will be 24.5. Okay, there's our 5.42 air-to-fuel ratio, running between 7 and 8,000 RPM without a high speed. Okay, examining this setup, we'll point out a few things. The air-to-fuel ratio calculator gives you the adjusted fuel to the motor, which is 109 gallons per minute. That's the fuel going through the nozzles. A lot of tuners tune by that, so that number is provided for in this case. Now, the pressure is a little on the low side, 41 psi for the 7,000 RPM value, and it creeps up to 54 psi. It's generally understood that fuel pressures should be in the 50 to 150 psi range. So one of the areas of improvement in this would be to possibly go down in smaller in nozzle sizes, a combination of smaller down nozzles and main bypass to get that pressure up. But again, keeping the same air-to-fuel ratio if you want. Now, we're not going to go into that at this point. However, we will demonstrate that, let's say the 5.42, that's a pretty fair air-to-fuel ratio for a high-end only motor. That would be a little bit lean for something like a sprint car or a drag car. However, let's explore what we can do in moving around. I'm going to put my main bypass down to 95 thousandths. Go ahead and get air-to-fuel ratio. Okay, that's a 508. That's a pretty good combination, especially for a drag car or even the high end for a sprint car. But again, it may be a little on the rich side for a top land speed or a water top speed racer. Okay, coming down here, let's start leaning that out. I want to start getting my pistons a little soft. So I had 100 in there and it was pretty good. So I'm going to put in a 105. Air-to-fuel ratio. Wow, 576. I've seen one dyno combination where they went as high as 6.2 and got their highest power output on injected methanol. So you could be creeping up to that 6-to-1 air-to-fuel ratio range for a high-end engine, and you might be okay. But this is the kind of thing when you start increasing that main bypass and leaning this down, you've got to really start examining your spark plug color at the end of each run to make sure you're not damaging it. The actual air-to-fuel ratio that you're going to run at is going to be very much dependent on the cooling system that you have in the racing vehicle. If this is a top-end engine used on water and there's no cooling limitations in it, and that engine is running with a lot of cooling water through it, you might end up being up over 6-to-1 on an air-to-fuel ratio and keep on adjusting that main bypass. Again, we're losing our pressure here as we're going up, leaning this out, so this would be a candidate for putting smaller down nozzles in it to try to get that pressure up. And again, you can go to the jetting calculator and recompute those as was demonstrated in some other videos. Thank you for your time.